So let's talk about some things, right? Starting our brand new section, and this is really essentially setting the tone for the rest of the semester at this point, at least for this course. Right, so up until this point, we have been looking all at thermodynamics and understanding heat engines, and we did all that stuff, and it was great, and it was fun, it was fantastic. I think a lot of people were like, this is great, this is old chemistry stuff, and other things that I've seen before, and there's a lot of fun review. Can't wait to keep learning more about thermodynamics. Too bad. We're done with thermodynamics, right? It's like a hard stop. Thermodynamics was then. We're not going to do anything with it now. It's kind of a very stark difference suddenly. And sometimes it actually gets put in some colleges will put it in the first semester course rather than the second like this, but we do things a little bit different. So why do I bring that up though? And why do I talk about this thing and setting the tone for everything else? Because the rest of the course, we're going to be studying almost entirely electromagnetism. And there's a couple lectures at the very end. I don't know what I'm going to do about them. We don't have time for them, certainly, because I lost 3 lectures from this semester. I don't know if I'll do bonus lectures or something like that. We'll see. It's really the basis here, starting with Coulomb's law. We are going to use this equation from now on, right? Everything that we do now keeps continuing on with us until the very, very end. And so that's part of the reason why exam 2, if you look on the calendar, it comes up pretty quick, realistically, right? We've got 2 weeks, and then that third week is going to be exam number 2. And the reason we do that is because all of this stuff counts. It matters. It's going to be used as the basis for the rest of our stuff from now on. So if there's a good time to be paying attention and a good time to say, hey, I need to sit down and make sure that I understand this stuff, now's the time. That also means that if any of this stuff is confusing or anything else like that, please get with me, right? In one way or another, in office hours or in emails, or if you want to meet, like do a video call one-on-one or anything like that, please. You know, that's what I'm here for. I want to make sure you understand this stuff. And that's why we set the exam early, so that there's a little bit of an incentive to make sure that we all understand this stuff before we get 5 weeks into electromagnetism and you're not entirely sure what charge is positive and negative. I have seen it before. I do not want to see it again. So please, there are some resources to help you with this stuff. Now, I do recommend watching Dr. Alexander's lecture on this one is a little bit longer than he normally has them, but I do recommend watching the first 10 or 15 minutes of that thing because he has a neat little demo and he talks about some of these things. But one of the things he does at the beginning is he kind of warns that up until this point, we've mostly been doing algebra. Right, mathematically, like we mentioned calculus, we said that we're using calculus and we took a couple results, but realistically, it's been algebra. But now that we're getting into electromagnetism, it is more mathematically rigorous, I should say, than what we've been doing previously. Real thermodynamics depends a lot on calculus, but we didn't look at that angle of thermodynamics. We looked at the algebraic form of it, but for electromagnetism, it's really hard to get away from doing calculus. So we'll have some of that here, right? And I do want to let you know that ahead of time, but I'll try and walk you through when we need it, what we need it for, and how to do it when we get there. So one of the things that we like to do for these things is we like to give kind of a little bit of a historical context, because realistically, the search for understanding electromagnetism is kind of what spurred modern physics as we know it, right? So thinking quantum mechanics and general relativity, or just relativity in general, not general relativity, but relativity in general, relative and general and special. It's a complicated bunch. A lot of that actually was kind of birthed from our understanding and finalizing out electromagnetism. Electromagnetism is kind of unique because it's like one of the only parts of physics that we feel really, really confident that we've got the answers, right? We understand the electromagnetic force very, very well. The other forces, maybe not as well. Particularly gravity is actually the weirdest one of the bunch. Despite the fact that we've known about it for the longest time, it's still the weirdest one of the bunch. So what I'd like to do is just kind of give you kind of a brief rundown of some of the things that we have seen to get us to this point in the first place, right? And we're first talking John Dalton had evidence that matter was discrete. What that basically means is that instead of being able to crumple up into infinitely small pieces, there were atoms and molecules, right? And at a certain point, you had the smallest building block of matter. Going from that, sometime later, Robert Brown, who, if you have remembered me talking about Brownian motion or the Feynman ratchet or anything else like that, that's what I'm talking about. What he basically saw, he was looking at pollen particles under a microscope. And what he saw was that he would follow one piece of pollen, and that single piece of pollen wouldn't just sit still. Bounce around every which way like this. Right? It was really weird. He concluded that even though we couldn't see it, there must be some sort of collision happening to make this thing divert its course so constantly. And that was kind of our first sense. Well, not our first sense, this was our second sense, that there was something else going on beneath the surface that maybe we couldn't see with a microscope. And then you had J.J. Thomson discovered electrons. We were able to create electrons, but it wasn't immediately clear exactly what they were. But by using a cathode ray, which is what old CRT monitors use to make all of those things, he took a cathode ray, he passed it through some charged plates, and he saw them be deflected, and he concluded that there were particles that held charge. And that's what all of this electricity and all of these charges were. It was because of these particular particles, right? And that was a big step. That was really cool, actually. But between all of these things, there was kind of a sentiment, and this was a little bit before 1900. There was kind of a sentiment that we were almost done with physics. We were very close to finishing everything. We're cleaning up the loose ends in electricity and magnetism. And I mean electricity and magnetism. They were separate at the time. We're about to figure out the rest of this atom nonsense. One of the planets behaves a little bit strange, but I'm sure we'll figure that out soon. We're probably just recording something wrong. For the most part, we really thought that we were about to have it. And to a certain point that they were even kind of denying more physics grad students. They said, go into these other fields. Why are you wasting your time here? We're done. We don't need more physicists. Then, you might have heard of the gold foil experiment. Rutherford and other people in the lab, not just Rutherford, but all of them in the lab, they wanted to test a few things. They had a very, very, very thin sheet of gold foil, and they took alpha particles, these new particles that we've isolated from nuclear decay, which we now know as helium nuclei, but at the time they didn't know that, and they fired some off of the gold foil, see what happens. There are a couple different ideas of what might happen. Maybe it is a sheet of matter, and all of them will be deflected back towards us. Maybe the atoms are very, very tiny or hollow or something strange like that, and it would pass right through. What we saw was strange. Rather than doing all of one thing, these alpha particles bounced in every direction. You know how if you drop a bouncy ball on a slope, it deflects off at a weird angle? That's kind of what happened here. What we were seeing is that instead of just bouncing in one direction, they were literally scattering every way. Which was... what does that mean? Right? That kind of flew in the face of a lot of our ideas at the time of what was going on with atoms. And what we really kind of started to conclude here was that the only thing that could do this is the electric force. Gravity is certainly not strong enough to cause a deflection like that. So it would have to be a very strong force, and we know the electric force is strong enough to do that. And if the electric force is strong enough to do that, and some of them are still passing through, That must mean that there's tiny points inside of these atoms, inside of this gold foil, that are very, very positively charged and kicking back against these alpha particles that fly in. And they're routed in such a way that if you hit one at the side, then it deflects off or something like that, right? That's why it's not just going one direction or the other. Some of them are still passing through, which means the atoms are still mostly empty space, but there is something in there that's very positively charged. And again, we didn't quite have all the answers yet. We didn't completely understand like neutrons and protons yet, but we were getting there. But then we also figured out, like when Frederick Soddy discovered isotopes, we started to get a sense that there's another particle inside of there, right? At the time, it wasn't clear. We didn't completely understand that there was more than just protons inside of the atom, but when different atoms had different masses, something else was wrong, right? And suddenly, a lot of things are very wrong. All of these things that we said were done. It's over. We finished it. Suddenly, it's like peeling back layers, and every layer has more issues. It's just a bunch of things all going wrong at once, and we're finally starting to see the gaps in our knowledge. So kind of continuing on with that, Niels Bohr, which is one of the biggest names, if not the biggest name in the development of quantum mechanics, had an idea about the structure of the atom that, okay, well, we know that atoms are neutral, and we've got an idea that electrons are in atoms in some way or another. So what if electrons spin around the atoms? What if the negatively charged electrons are attracted to the positive nucleus and they spin around like the planets do? That made sense. Because at the time we had a good idea that the Coulomb force kind of looks like gravity, so what if it's like the solar system all the way from the top to the bottom? That'd be kind of a neat result. And that made sense because if it was stuck into specific orbitals, atoms were doing this really crazy thing where they only liked certain colors, right? If you're looking at like the emission spectrum from hydrogen, there are only specific colors that it actually absorbs. Going to have some sort of red color, a cyan color, and then 2 violet lines, or 3 violet lines if you've got a really bright source and good eyes. At least in the visible range, right? And that matched up pretty well. If we took that conceptually, that matched really well. That did a really good job of explaining why we only see certain colors of light, and every atom has its own unique set of light because every atom has its own unique structure of electrons. The problem with that is that if you have a charge spinning around like that, it actually emits energy in doing so. The spinning charge will continuously emit light, kind of like how a microwave works on a basic level. And because of that, if it's constantly emitting light and losing energy, then that orbital gets smaller and smaller and smaller until it collapses into the nucleus. So kind of immediately we knew, all right, this doesn't work. But it's still a very common model because it does a great job of conceptually explaining the structure of atoms and why they only emit and absorb certain colors of light. So we kind of hold on to it even though we know it's slightly wrong. So going beyond that, right, more experiments that were very important. The Stern-Gerlach experiment showed that nuclei have spin, an angular momentum, and even more, a magnetic moment. They interact with the electromagnetic force. And that was a really kind of cool thing because that basically established that all of protons, neutrons, and electrons are what we call fermions, or particles with spin. Particles specifically with half spin. Which is a thing that we don't need to worry about what that is. But if you remember from chemistry, like the spin up and spin down, those are half spins, a plus 1/2 and a minus 1/2 for all the electrons. And that was a really big thing. And here on the right, you can see those beautiful, beautiful physics memes that we love to pass around. You're missing out if you don't look up physics memes. Going beyond that, we have seen some of this stuff before. If you're downloading the slides, one of the dates in here was wrong. It should be 1924 that Heisenberg formulated the uncertainty principle, which we looked at last semester a little bit, right? And we realize that even though electrons kind of behave like they're spinning around the atom, it's not quite what's happening, but it kind of is, but not really. And it's actually a probability cloud, but technically it still spins. It's in a weird in-between state, right? And if all of this sounds confusing, that's because quantum mechanics is pretty confusing. There's a lot of quotes that it's essentially the study of the absurd. There's a lot of strange things in here. And that's a lot of actually on that last slide why Einstein and Bohr bickered back and forth so much together, because they disagreed fundamentally on what quantum mechanics was trying to do. And there's a lot of cool history behind all this stuff. There's just so many cool things in here, seeing the development of all these things, all of the essentially the renaissance of physics around this time, and all the great discoveries that were being made, and the, shall I say, very eccentric personalities that went along with a lot of those discoveries. It's a fun read. If you ever go through any of these biographies or anything like that of any of these old physicists and these old scientists, it's really something. So, moving a little bit closer to today, eventually we came up with the Standard Model, and this is where it gets even more confusing, because there are two more forces besides gravity and the electromagnetic force. There's the strong force and the weak force, and those, we're not going to talk about those. I will mention them occasionally, but we're not going to study those in any real detail. But then you've got these other particles. It turns out that the protons and the neutrons, we thought atoms were the smallest thing, but no, it turns out there's particles that make those up. They're called protons and neutrons, or nucleons, broadly speaking. And then we found out that the protons and neutrons are made out of particles. They're up quarks and down quarks, and sometimes you get the charm and strange and top and bottom, but there's all sorts of weird things, right? But the Standard Model is essentially a description of all of, as far as we know right now, the building blocks of matter and the universe as a whole. And we're still not finished, right? I think you guys probably know this at this point, but we have not finished science. It's an ongoing process. There are still some really big problems that we have yet to solve out all the way. 4 of them are down here in the bottom right of this poster, if you'd like to look more into those. And realistically, we're not going to look into a lot of this stuff, but it is kind of cool that essentially the study of understanding electromagnetism has led us here. It all started with a couple things didn't quite match up, and some particles were flying off in a weird direction that we didn't understand. And so much was born out of just that stuff, right? And here's a little bit of a focus on what we're actually going to look at, specifically the electron. We like those. We'll talk about those plenty. And then the electromagnetic force is the other piece that we'll focus on a lot. So, a lot of history, right? Now, talking about that electric force, or the full electromagnetic force, remember that when we started this thing, and we are going to kind of approach this a little bit historically, when we started this thing, we knew that electricity and magnetism had a relationship, but we weren't entirely clear that they were actually part of the same force, right? They're two different perspectives, and I mean that kind of literally, actually. They're two different perspectives on the same force. So we're going to start with electricity, though. And this goes back before any of the stuff that I was looking at here, right? Actually back to the 18th century. We've had a good idea of what electricity has been doing for a fairly long time now, relatively speaking. But Charles Coulomb was the first person that really started to describe the interaction between charged particles. You might know that if you wear socks and rub your feet a bunch across a lot of carpet, you'll build up a static charge, right? Or if you comb your hair a lot, you'll build up a static charge and your hair gets all frizzy, right? And every single day, there's nothing I can do to get rid of it. But anyways, what's happening there? Well, certain materials are not so careful with how they hold their electrons. Those electrons are maybe not so tightly bound to the material. And when that happens with a little bit of mechanical force little bit of extra heat and a little bit of movement, those electrons are actually separated away from those particles. And it's not a big deal. If something becomes a little bit charged, ionized in one way or the other, it's not a big deal. That happens all the time. And now these free electrons will move to whatever is causing that motion, right? And certain materials like to pick up more electrons. Certain materials like to give away their electrons. Some don't care. The human body, in particular, is a poor conductor, but a conductor. And that's why we can pick up a bunch of this charge and then touch a doorknob and shock ourselves, or hopefully somebody else. But when we were first studying this stuff, when we first started building up charges on certain things and everything else, we had an idea of what charge was. We said, okay, well, we see these things interacting, right? The balloon, when moved around on your head, sticks to your head afterwards, which, again, here's another plug. Watch Dr. Alexander's lecture because he does this. But what he started to discover was that it actually behaved a lot like gravity did, right? It depended on the magnitudes of the charges, and it also scaled with the distance squared. And that was kind of a cool result because basically, okay, well, we know about one force, gravitational force, and it goes like this. And if this second force that we're talking about behaves in the exact same way, that's a pretty cool result. That's kind of validating almost, right? That it would behave in the exact same way as gravity. So what he did, he realized that relationship and he drew a parallel with that, right? If you remember that gravitational force equation, well, here is the electric force equation. And now we're going to talk about this a little bit differently, though, because in the case of gravity, mass goes from 0 to however big you want it to be. It's never negative, and gravity is always attractive. Electric force is not quite the same. Electric force can be attractive or repulsive, and that depends on the charges, which can be positive or negative. So it's a little bit more complicated to watch, right? The way that we're going to treat this, or at least the way that I'm going to recommend you treat this, is that when you're solving out this force and you're looking at this direction, you're not thinking about the direction immediately, or rather treat the magnitude and the direction separately. That's why we have these absolute value signs around Q1 and Q2, because what we're trying to do is we're just trying to say take the magnitude of the charges, find the magnitude of the force, look at your picture, figure out what direction the force goes, right? And then deal with the positive and negative. Because if you've ever heard opposites attract, lock that down. That's absolutely true here, and we're going to use that for the rest of the semester. Positive and negative charges pull towards each other. Positive and positive, negative and negative, they both push away. They're repulsive. So, find the magnitude, draw the picture, figure out if it's going to be attractive or repulsive, draw it, right? And it's always going to go, you can see it's on a line, right? It's on all one line together. That's where the forces go, all that good stuff. So, let's try it out, no problem, right? And then we've got our brand new constant, too. 8.99 times 10 to the 9th. Instead of capital G, it's capital K. So, let's say I have 2 protons in a nucleus, and this is kind of accurate. They're about 2 femtometers apart. So that's a 10 to the negative 15. What is the magnitude of the electric force on one proton due to the other? And I will tell you that protons and neutrons, or not neutrons, neutrons don't have a charge. Protons will always have a positive 1.6 times 10 to the negative 19th coulombs, which is our unit of charge, right? That's our standard unit of charge. Electrons have negative 1.6 times 10 to the negative 19 coulombs. So, and you might notice one thing if you're looking towards the Canvas questions and everything else, that the Canvas questions are not whiteboard problems today. It's a survey. I'm trying to figure out what you guys would like to do with the rest of the course. We'll get into that sometime later. I need the results to come in from you guys, and I'll take a look at those and see what the general consensus is one way or the other. But anyways, back onto the problem here. Answer in pounds if you'd like. I'm not super concerned about it. It just gives kind of a neat sense for how much force it is, because we use pounds all the time for things. But find that electric force, and then find the gravitational force, and see how that compares. So, I've got 1 proton, 2 proton. There is a distance between them, 2 femtometers, or 2 times 10 to the negative 15th meters. So we're going to call that distance r, right? And I'll actually come back to this idea why we like to use r rather than something like d for distance, as we might normally think. There is a reason for it, but it kind of comes when we start talking about fields. So each proton has the charge of a proton and the mass of a proton. So it's a plus E, and then a mass of proton. Plus E, mass of the proton. Every single proton has a charge of 1.6 times 10 to the negative 19th coulombs, and a mass of 1.67 times 10 to the negative 27th kilograms. Every single one, right? All of the up and down quarks that make them up are all identical as well. The only time you could get something weirder than this is if you mixed in one of the other quarks, like a strange quark, in place of, I think, the down. Oh, shoot. I don't know my particle physics well enough to come up with good analogies like that, but we're never going to consider anything like that. That is way beyond the scope here. We'd have to worry about radioactive decay and increased mass and a bunch of other nonsense that goes on. So, none of that stuff. We're always going to assume that the electron and the proton, they always have the same charge, they always have the same mass, right? If I talk about 10 electrons, 10 times the charge, 10 times the mass. So, that all being said, we're going to make good use of our equation for the electric force, right? What we can do is we can just say, okay, electric force, we saw from the last slide, is going to be K, Q1, Q2, over R squared. Then, we can say, okay, well, Q1 is positive E, Q2 is positive E, right? That makes the whole thing a little bit easier. Let's go ahead and, you know what, we'll plug all these numbers in. Why not? And then squared. And then, whoops, I said numbers here. Right, so we've got all that stuff. And it turns out we've got a lot of orders of magnitude floating around here, but when we plug all of them in together at the very, very, very end, we get 57.5 newtons. Which, I want you to think about that for a minute. 57.5 newtons is not a crazy amount, right? In fact, that's about 13 pounds. That is the force. These two, you can't see an atom with a microscope. I want you to kind of conceptualize that. You can't see, atoms are too small to view with a microscope. Protons are, I'm going to say probably, this is an overestimate, 1,000th of the size of an atom, probably smaller. These subatomic particles are exerting 13 pounds of force on each other. And this is assuming there's only two. If we mixed in a third, now we've got more sources where this force, more places where this repulsion is going to come from, right? So this would be the case for a helium atom, but think about all those other crazy atoms that exist out there, right? Up to 118 protons in one nucleus. Naturally, the distance does increase a little bit, but that many more particles that are going to be repelling off of each other, that's a lot of force. So, here's our answer for part one here, right? Now, the question then becomes, we know that atoms don't just explode. we know that the protons don't spontaneously shoot out and cause all sorts of issues, or else there'd be a lot of problems in the world. So something else is there to keep them in place. There's another force keeping them together. Could it be gravity? Let's find out. And I'll leave myself a little bit of space because there is one more number that I kind of like to show. F of G, M1, M2, and it's the same R, so that's nice and easy. But now, and I always need to look up my numbers on this one. I always forget what capital G is. 6.67 times 10 to the negative 11th. And again, I said the masses of all these things are the same. So we're just going to see this as 1.67 times 10 to the negative 27th squared. This is not a good sign for a big number. We get something like that. And by the time we actually go through and plug all of these numbers in, 4.65 times 10 to the negative 35th. It ain't gravity. Not by a long shot. This is way beyond the point that I would say it doesn't matter, right? It's such a small force. I could multiply that by 10 to the 20th, and I would still say there is no impact that force has whatsoever. Gravity is the weakest force. I know we have a weak force, but gravity is really puny. So much so to the point that the ratio of these forces per unit, that the electric force, the gravitational force, it's about a 10 to the 36th difference. And I want you to think about some of the circumstances you might see this, right? So I'm kind of letting you know ahead of time that the electric force and magnetic force, right, they're two sides of the same coin. Your fridge magnet has enough force to overcome all of Earth's gravity, and then some. And it's not even that the magnetic force is what's holding it up most of the time. A magnetic force is pulling you in, and then friction is what's doing that pulling up. So it's not even the full magnitude of the magnetic force. It's a fraction of that force because that's what comes out in friction that's stopping this thing from falling down, and it's helping you hold up your papers or something like that, right? I've got a bunch of coupons up on my fridge right now. The electric force is an incredibly strong force. But probably more of a statement is that gravity, in comparison, is incredibly weak. What we actually need in this case is what's called the strong force. And it's not something that we're going to talk about much in this course, but it's essentially the force between nucleons that stops this crazy repulsion between the protons from causing the atoms to explode. It's why there are neutrons inside of the atom. They're needed for stability, right? Because the neutrons interact with the strong force, but they don't have a charge to continue that repulsion. So, it's a fun number. And the last thing I did want to show with this as well is if we imagine for this much force, for this small of a particle, imagine what the magnitude of the acceleration would be. 57.5 divided by 1.6 times 10 to the negative 27th, you are getting something on the order of magnitude of 10 to the 28th meters per second squared. They really want to get away. Real bad. So the strong force has to be incredibly strong to actually keep these things together. So this is a topic that we're going to come back to a few different times, right? But you can polarize certain objects. And let's talk about what that really means, right? And I was kind of mentioning before that certain materials are happy to give away electrons, certain materials are happy to take electrons. Let's imagine for something like a metal. Inside of a metal, all of the electrons are allowed to float around, right? They're not actually tied to any one single atom. It's just it's a big sea of electrons, and there's some inner electrons that stay nearby, but all the outer electrons are free to just float back and forth between all the different atoms. So, if I was to take a positive charge and bring it close to one end of the metal, all of the electrons lose their minds and say, look at that positive charge, I need to get there, right? All of the electrons are going to group up towards that positive charge because they're attracted. That leaves a deficit of a bunch of electrons on the right side of this thing, and we end up with a polarization inside of the metal. One end has a bunch of electrons, so it's going to be more negative. The other end doesn't have as many electrons, it's going to end up being positive. If there's no external charge, everything's kind of floating around neutral or so. While that works on a very large scale with metals, regular atoms can do this as well, right? Because the fact that the positive charge is in the center and the electron cloud is around the outside of this thing, that means that if I bring any sort of external charge, that cloud is going to feel a little bit more force than the central charge will, right? And it's allowed to kind of shift one way or the other. If I bring another positive charge, you might see, for example, the negative charge wants to pull a little bit closer towards the positive charge, whereas the other positive charge is going to try and get away from it. And what happens when you bring this external force like this and you have this split of positive and negative from something that is neutral, so the neutral atom becoming a polarized atom, you get what's called a dipole. And a dipole is essentially a combination of a positive and a negative charge stacked right together, right? And we've got a lot of special equations that are going to deal specifically with these. I'm going to come back to this idea a few times, but I figured I would tell you right now, talk about it a little bit, and then we'll start to hit it in detail sometime later. But you can see how the dipole can form from some of these things. And this might describe some of the things that you see in reality. Let's try another problem with this stuff, though. So, now, instead of just 2 particles, I have 3 charged particles. So what I want you to do is find the magnitude, the net force, on particle A, summing up these 2 forces. Okay, so if we're focused on particle A, right? A is not going to act on A. That's just not how any of our forces have ever worked. The block does not exert a force on itself. Instead, we've got to look towards these other 2. So if I'm looking at particle C, right? Particle C has a positive charge, particle A has a positive charge. Opposites attract, but like charges repel. And that means that the force from C, and I'll literally just call it F of C, is going to be pointing in that direction. And while we're here, let's not forget our good picture practices. Draw our axes. So the second thing we can do is we can look at particle B. What's that thing doing? Well, opposites attract. So force from particle B is going to go like this. Right? Those are our 2 forces. So now we just need to calculate these things individually. And let's go ahead and start with force from C, because I drew that one out first. So again, the way that I like to treat this is I like to find the magnitude first, and I'm going to deal with thinking about what the direction of this thing is after I've already figured that out, or while I'm drawing the picture realistically, right? I'll add the positive and negative or the components later. So what I'll do is I'll say F of C. This is K, absolute value Q1, absolute value Q2, all over. Now, I'm going to call this, well, let's just leave this as 2 centimeters. So let's say 0.02 squared. We don't need to complicate it right now. It's pretty easy to see where each one's going. We do all that stuff. I'm going to plug in some numbers now. So 8.99 times 10 to the 9th times, I've got 1 nanocoulomb and 4 nanocoulombs. So 1 times 10 to the negative 9th and 4 times 10 to the negative 9th. There's a lot of exponents in these. It's the biggest problem with it. So while it's maybe not necessary to solve completely in variables at this point, it's still just a lot cleaner and faster if you do. I promise. Still over my 0.02 squared. Right. And then what I can do with all this stuff, I can say, okay, let's go ahead and plug in everything to our calculator. And what you should find, at least what I found, was 8.99 times 10 to the negative fifth. It's a little bit different from what we just found in the last problem, but at the same time, in the last problem, we also had a much smaller distance, right? They were really packed on top of each other. So the last thing that I would do here is I would say, okay, well, I look at my picture. Here's my y-axis, my x-axis, and I see f of c, I see is pointing to the left. So if I was to write this as a vector, f of c is going to be a negative 8.99 times 10 to the negative fifth. Got stuck on that for a minute there. And then specify direction, I hat. Or I can call that, sometimes I call it x hat. It doesn't matter. It's just convention. So, next thing that I want to look at is f of b. And I really just end up going through the same process here. You know what I should have done last time that I absolutely didn't do? That's not 2. It's 3, right? It should be 3 because we were looking at the difference. We write out Q1 and Q2, but we were looking to charge 3 for that one, or C rather. So, looking at the same thing here now. Now it's over 0.01 squared. And again, I take a bunch of absolute value signs, so that's why it seems that a negative sign just kind of vanishes here. It's positive 1 times 10 to the negative 9th again. Plug in all that stuff. What do we find for this number? We should find, what do you know? 8.99 times 10 to the negative 5th. It feels like a setup. But anyways, we look back to our picture. We say, okay, well, clearly I see f of b as I drew it as pointing to the right. So now this should be a positive 8.99 times 10 to the negative 5th. I hat. F net. F of b plus f of c is equal to 0. Anyways, you might have noticed a lot of 191 stuff is coming back to haunt us, right? Or to bless us if you had a great time in that course. Take your pick. In either case, it's stuff that we need to know, and it's stuff that we need to be able to use. So if you remember a lot of our stuff with forces and free body diagrams and vectors and acceleration and all of that good stuff, the most important bits have been saved at the top of the equation sheet. If you've looked at that thing, there's a section called Good Stuff from 191. Can you guys still hear me? Okay, I'm just going to hold like this for a little bit. Yeah, yep. Okay, this keeps happening. I don't know why. I scream. Let's get to the next problem, and I'll get it reset while we're working on that one. So in the meantime, here's me staring into the screen. So, quick vector review, right? From some of the things that we have seen before, right? We might remember things like direction and magnitude, and that these are very important things of a vector, and that we can split it up into vector components, right? A of x times I hat plus a of y times j hat. Or we could write that instead in terms of a cosine of theta plus a sine of theta, assuming that our angle theta is always taken from the positive x-axis, this one right here. If you take it from anywhere else, this equation starts to fall apart. But there's a lot of different things we can do with these things, right? If you haven't seen this stuff for a while, give yourself a quick refresh. We're about to use these things in a little bit, so it's some good practice there. But remember that there's a lot of things that we could do with vectors. They're very useful. If we would like to add or subtract vectors, there are two different ways to do that, technically. We could do it graphically by taking tiny little paper cutouts of the vectors and then stacking them together and figuring out where they end up. But I'm willing to bet that you're probably not just going to want to do that all the time. So instead, graphically it's helpful to visualize, but we're more often going to find exact numbers by doing it, solving in terms of components, like this, right? So remember that if I'm adding up two vectors together, that means adding their components, not their magnitudes. If I'm subtracting, that means I'm subtracting their components, not their magnitudes, and that's an important distinction. Now, you might remember as well that there are two, here's my air quotes because you can't see them, multiplication things that I can do to vectors. Specifically speaking, the dot product and the cross product, which aren't quite multiplication, but kind of, but not quite. We will end up using those as well, but for now, I'm just focused on the addition. So, let's try this. I have two vectors, A and B. Let's take a vector f that is equal to a minus 4 times b. Find the components, find the magnitude, find the direction. All right, so time to start looking. Let me pull up. There it is. I just like to have the numbers in front of me, just in case I say something dumb. So I'm not going to draw these things out. I'm not going to do this graphically because I would have to draw out my axes and make sure that everything's accurate, and that's begging for trouble, right? Instead, like I said before, I like to do this with a bunch of numbers, a bunch of components. So what we have is a vector A. And a vector B. Ooh, I looked away for a second and I shouldn't have. We're asked to find f, which consists of a minus 4b. So I'm going to break this into individual components first, because that's probably the easiest way. Start with f of x. So it's going to be x component of a minus 4 times the x component of b. If we do the same thing with f of y, now it's negative 2 minus 4 times the y component of b. Put it all together into component form, just because it looks nice that way. We've got all that good stuff, right? Now, if we wanted to find the magnitude, that's not so bad. And if I write the magnitude, it's just f is equal to the x component squared times the y component squared. And if there was a z component, we would just put that in there as well, right? Pythagorean's theorem keeps going up and up and up and up and up, however many dimensions you have. We should find something like 27.2 is my total magnitude. And then I can do arctangent to find my angle, theta. Here's a problem. You might throw this into your calculator. You might not get an answer that you expect to see. Specifically, if I put this into my calculator, what I would find is a number like, where did it go? Negative 53.98. That's not a positive angle from the x-axis. Instead, what my calculator has done for me, whether or not I asked it to, here's my x and y axes. It has given me, I know I'm somewhere, realistically, I know I'm somewhere down here, right? I am a positive x but a negative y. So I'm somewhere down in this quadrant. My calculator has informed me that this angle right here is 53.98. And that's okay. But if we're following standard angle, we need this one. And this one is going to be 360 minus our answer in red, so right around 306 degrees. Right? Be smarter than your calculator. And remember that when we do a lot of these things, it's always a possibility that it's one of two answers. Keep that in mind. Right? This answer could have just as easily, if we would have put in instead this angle to my calculator, it could have just as easily given us the same answer. Fun things on vectors that we need to pay attention to, right? If we are trying to fit this all together with how we're talking about solving a lot of these problems, what we are going to need to do is deal with this graphically as well, right? Realistically, since we are dealing with the fact that we are trying to not confuse ourselves with what's going on with the sign of the charges and whether it's attractive or repulsive, just from the math alone, we need to find the magnitude, draw it out on a graph, figure out where it's going to be and how we're going to break that into components. That is probably going to be the easiest way to do this, right? The reason being that there is technically a mathematical way to write this out so that it takes care of it for us, but it looks like this. And I'm going to tell you right now, you don't want to deal with it. I don't want to deal with it, and I didn't want to deal with it when I was taking it in grad courses and everything else. It's just not worth it, right? Let's stick with our pictures. I promise it's probably going to be the easier way to deal with this. So, calculate out the magnitude, or rather, draw it on a picture, calculate the magnitude, then split it into components. That's our order of solving these things. So, speaking on some of these things, right? If I have 4 particles, all with positive charges, I am looking at the net force on my charge on the bottom left. What's it going to look like? Do we have any guesses? Two answers so far. Can I get a third? Okay, so let's take a look at this. Remember, like charges repel. So if I take these things in order, top charge on this charge down here, right? I am expecting to see something like that. Can you guys not see my cursor? Is it not showing up on the screen for some reason? That's weird. If I am looking at now the top right charge, I'm going to get a force that looks like this. If I'm now looking at the bottom right charge, I'm going to get a force that looks like this. All combined, I know I'm going to end up somewhere in this direction, right? It might not be exact, the angle might not be accurate, but I know I'm going to be pointing in that relative direction because all of the forces are repulsive, right? That's what we're going to end up with here. So B should be our correct answer. Okay, so let's try a problem with this stuff. What we have is 3 charges, now no longer just on a line together. So what I'm going to recommend is that to solve this problem, you should draw this picture out. Please just draw this picture out. Find the magnitude of the net force, or just find the net force on this particle down here, on Q3. That's the one that we're interested in. Right, go ahead and find this in component form. That's probably the best way to do it. Then you can find the magnitude and direction from there once you've done that. But keep in mind, you cannot just add the magnitudes. You can only add them if they're pointing in the exact same direction. And I will tell you right now that the 2 forces acting on my Q3 are not pointing in the same direction. But anyways, let's take a look at this one. So I'm going to kind of treat this like I did last time, right? I'm looking at everything happening to my bottom right particle here, and what I'm going to do is just piece by piece, I'm going to draw out the different forces and where they should be going. So before I get all the way into that, though, the last thing I am going to do is I do want to draw this line right here, right? And let's make it dashed, because what we have is a distance between these 2 particles that is not written on the picture. It's a little bit obnoxious, but that's okay. We can deal with that. What I'm going to do is I'm going to call this distance R13. maybe dash, nah, it's harder to read like that. R13, and that's the distance between 1 and 3. Right, so comparatively speaking, R23 would be this one right here. Right, and that'll just help me figure out where this thing is going to go, and that distance, while I'm talking about, let's draw these things first. Sorry, I'm trying to think of the best order to do this kind of on the fly. So, I know that between 1 and 3, they are opposite charges, so they are going to attract. So my force vector will point this way. Call it F1. I know my other one. They're like charges. They're going to repel. So F2 is going to point like this. Here's the nasty bit. F1 is split between X and Y. F2 is nice and easy, right? It's just pointing in the negative Y direction. But we do have to figure out what's going to go on with F1. So what I'll do here is we're going to start by saying, okay, let's take this angle right here as theta. And we need to find what R13 is supposed to be. So, and rather, let me do that in black. Theta. So R13, I'm looking at the hypotenuse. If I do this in centimeters, this is 1 centimeter plus 3 centimeters squared. Square root of 10 centimeters. So we've got that, and then we can also do a similar kind of thing for theta. Take arctangent of 1 over 3, and we should find an angle like 18.43 degrees. So now we've got that information, right? We really needed that because we're going to need to split this thing up. So the first thing we do, we've drawn our picture. We know what direction it's going to be pointing in, but let's focus on finding that magnitude first. So if I want to find the magnitude of F1, it's going to be K, and it's just 8.99 times 10 to the 9th times 15 times 10 to the negative 9th. And again, I take a bunch of absolute values. That's why this negative 10 turns into a positive 10. All of this is over R13 squared. R13 squared is 10 centimeters, or 10 centimeters squared. Oh, I messed this up last time, didn't I? Yeah, I did. I did something wrong in the first lecture, and I'm just now realizing. You know, it's easier than that to leave this as, before I do something dumb. 3.162 centimeters. I failed myself in dimensional analysis and keeping track of my units proper. So let's say 0.03162 squared. Anyone sticking around from section A, which I don't think there are any, but if you are, I apologize. So we plug all this stuff in. We find some sort of net force from the, or not a net force, but a magnitude of the force here. And that should be something like 1.348 times 10 to the negative 3rd newtons. Okay, then we need to break this thing up. We need to actually put this into the terms of components. So what I can do with this, I'm going to keep track of what's going on with my picture. So all this stuff in red is for F1. I'm going to say, okay, f of x, I know it's a negative. I see it on my picture, right? This is y, this is x. I know it's going in the negative x direction. And even if my angle is not necessarily coming from the positive x-axis, I know what number I expect to see. And as long as I know what number I expect to see, I'm in a pretty good spot. So what we can do then is say, okay, well, this is just F1 times cosine of theta. When we do that, negative, 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 negative. I made that whole big point. When we do that, we end up finding that this should be negative 1.279 10 to the negative 3rd. F of y is going to be a positive. We see it pointing up. positive 4.262. 10 to the negative fourth. Okay, now we've got those two in components. We move on to what's going on with F2 here. F2 is nice and easy, right? So much easier to deal with because it's all just pointed in the negative y direction, so I can just immediately go to this. Divided by, now it's 0.01 squared is equal, plug all these numbers in. We should find, for 2 on 3, this is negative 4.49, well, right here, the magnitude is positive, 4.495. 10 to the negative third. The actual vector points in the negative y direction. Like that. Okay, so once we're there, we've got that. We've got F1, we've got F2. We're looking for F net now. We're going to combine all these things together. I add up my x components. I add up my y components. What I should find is F net is negative 1.279, 10 to the negative third, I hat, minus 4.069 times 10 to the negative third, j hat. Can find the magnitude, x squared plus y squared. I should find this total magnitude as 4.265. 10 to the negative third. I should find my angle from positive x-axis to be 252.5 degrees. That comes from, I would take arctangent for that. If I'm taking my x component, my y component, your calculator is going to tell you something between 0 and 90. But we know that this is pointing in the negative x and the negative y direction. So we would need to add 180 to that. Because your calculator doesn't distinguish that there should be two possible answers from this. It just goes with the closest angle to 0. This thing is expecting to see, I think, 70? 60? Something like that. We know that our actual vector points down this way. Calculator thinks it's pointing this way. Because those two negatives will cancel out and your calculator just doesn't distinguish between these two possible answers. Okay, so this last one, so without any further delay, to see if I can get done by 4 here, I want to go ahead and work through this thing. Need to zoom out to actually move it, don't I? Okay, so free body diagrams are really going to be the name of the game here. In a problem like this, what I can see is that it's mirrored over the y-axis, right? Anything going on with the left side is going to be pretty much equivalent to what's going on the right side. It's just flipped directions, right? So I don't need to actually pay that much attention to both of these at the same time. Rather, I'm going to focus on just one. But we need to draw a free body diagram. So let's look at the things that are actually acting on this one. I'm going to look at the right one. So first, I've got tension from the rope. I've got gravity. So tension vector, gravity vector, and finally we also have from the electric force. And while I'm here, it's never a bad time to specify my axes. And I'm going to make one more thing here, and I'm going to mark down my distance, r. So something like this, and actually, in fact, I'm not going to go from the ends of the particles, I'm going to go center to center, right? Just like gravity, it acts from the center of the particle. So let's call this total distance r, the distance between the two charges. Okay, so we've got our work cut out for this in this one, and we're going to have to draw out essentially all of the forces acting in the x direction, all the forces acting out in the y direction. We know right off the bat that nothing is moving. F net is 0. So, I can say then f of x is 0. And what goes into f of x? Well, I see f of e pointing in the positive x direction. So I'm going to start out with a basic drawing of that thing. And I see that it's slight, but there is a component of the tension pointing in the x direction as well. So that's going to be minus t sine of theta here. Sine of theta is the x component pulled off from this tension in this case. And then I can do the exact same thing with f of y. So what I'll see here, I've got now positive tension. Oh, first it's equal to 0. Now it's a positive t cosine of theta minus gravity. Nothing new here, right? Stuff that we've seen, albeit a little bit long ago. Okay, well, here's the thing. They don't tell us what that distance is r, right? We're not entirely sure what that distance actually is yet. So f of e is a variable that we actually don't know. Tension is also not a variable. Okay, well, maybe we could use a system of equations to solve these two together. Here's the problem that I'm going to run into. Not only do I not know r, and I not know t, I don't have theta either. So we've got a work cut out for us, right? With 3 unknowns, this problem's impossible to solve. We need another equation to tie everything together. Luckily for us, geometry is maybe not a kind friend, but a friend. What we can do is I'm going to just draw out one of these triangles one more time. But now I'm going to kind of tip it on its side so it's a little bit easier to visualize. If I take this triangle right here, and again, it should be a right triangle. Ignore the fact that there's a little bit of deviation from that. But this angle right here is theta. This distance right here is 1 meter, and this distance right here is half of r. There is a relationship between theta and r. So it is going to be easier for us to say, okay, sine of theta is equal to r over 2 over 1, leg over hypotenuse. So better yet, let's just rearrange this in terms of r. R is equal to 2 sine of theta. And I promise it's the easier thing to do here to solve this out for r than it is to solve sine of theta. So once we have that, we can go back up to our f of x equation. And I'm going to write into this thing, okay, we had k, it's the same charge on each of these, right? Q is 100 nanocoulombs and 100 nanocoulombs. So I'm just going to call this q squared over. Now we have r squared becomes 4 sine squared of theta minus t sine of theta. And you might be looking at this and saying, okay, congratulations, you have made the problem more complicated. And yes, but it's really the only way out here. So now, if I look at these two things, I have q. K is a constant. Theta, I'm looking for that. Theta, t. Okay, there are only 2 unknowns at this point. This now is a solvable system of equations, but it's going to be a little bit nasty. The first thing that we're going to have to do, and that I see here, I see a t sine of theta, I see a t cosine of theta. I'm going to rearrange both of these equations. So this is going to become t sine of theta is equal to k q squared over 4 sine squared theta. Likewise, a little bit too long. Go something like that. This will turn into t cosine of theta. It's equal to mg. Now, divide these two. I'm going to take the top equation divided by the bottom equation, and I can absolutely do that, right? That is totally fine. It is one of my algebraic tricks. So if I take t sine of theta divided by t cosine of theta, the t cancels out. Nice. And we get tangent of theta. Now we are down to an equation with only one unknown left. What's the problem? Well, how do I solve out tangent of theta times sine squared of theta? I don't really have an answer. Computers can do it. I can't. So what I'm going to have to do to actually get a reasonable response on paper for this thing, I'm going to have to take the small angle approximation. The small angle approximation says a few different things. Tangent of theta, as long as the angle's small. As long as the angle's small, tangent of theta is supposed to be sine of theta over cosine of theta. And if theta is small, cosine is almost 1. So tangent of theta is almost just sine of theta. This is not the sine of theta is equal to theta version of this. Tangent of theta is almost sine of theta is probably the most accurate form of the small angle approximation that you can take. So that's the one that we'll go with here, right? Tangent of theta is almost equal to sine of theta, so let's just plug that in. And if we do that, we can multiply over, and what this turns into is sine cubed theta is equal to kq squared over 4mg. Yeah, it should be sine of theta. Let me make that a little bit more clear. That is something I can do on my calculator. Take a cube root, take an arc sine. We don't need to do, well, I'm halfway through writing this thing. We might as well. To the 1/3 power. Theta is equal, I need the number, 4.42 degrees. So it's a fantastic problem. I love to work on this one. I think it's really, really neat. It ties in a lot of our old 191 ideas with all of the stuff that we've just seen today from 192. Great problem altogether. But I think that is going to close out our lecture for today. Next time, we're going to continue on talking about the electric forces and all of the stuff that plays into this, and kicking off the rest of electromagnetism.